Assalamu alaikum. Welcome to lecture 23 of natural language processing. So we are into the last couple of weeks of the semester, and so we will be kind of wrapping up our discussion on the transformer today and then moving on to the discussion on machine translation with an introduction to the encoder-decoder model. So this is the 23rd lecture, and we will have the 24th lecture on Thursday, and then 25 and 26 next week. So we might take 27th lecture on the third week from now. So let's see. So we still have some content to cover, but looks like we won't be able to cover everything. For example, especially chatbots and summarization in detail. So, but let's see. So today I will start again with discussing the transformers, and then we'll talk about some applications of transformers, and then we'll move on to machine translation. So that's the agenda for today. Any questions? So let's discuss the transformer again. So transformer is basically a sequence processing model. It is not inherently sequential. It can be processed in parallel. So that's the biggest advantage of the transformer. And it's based on the idea of attention. In other words, it tries to capture the relationship between different positions in the sequence through attention, which is computed through a notion of relatedness. And that notion is, of course, quantified through the dot product. So that's basically the gist of the transformer. I will quickly write the basic equations of the transformer, and then we'll continue with that. Actually, the transformer that we introduced last time was what is known as a causal transformer, or a backward-looking transformer. And we will see the difference today, why it is called that, and why other versions are not called the backward-looking. So let's first write the equations quickly. So let's say we have a sequence of length t, and all those sequences with their embeddings are placed in this matrix X. So this matrix X is basically of length, it's T by D, where T is the of sequence and D is so embedding length. So each word in the sequence or each unit in the sequence is represented by embedding of length D. Okay. And then we have some parameters for. So we are discussing one transformer block with a single head. And you can have multiple head, and I will explain that later on. So we have a number of parameters. We have W, Q, and then we have W, K, which is for key. Both of these are of sizes D, which is the input size, input embedding size. In general, this could be DK. This second dimension could be different from D. And usually in practice, it's going to be less than D. Let's say if your input embedding is, let's say 512, this DK would be, let's say 128 or 64. So in other words, we're also reducing the size. Okay. And then we have another parameter for the value role, and this is D into dV. Again, we have a different size for this, and again this is smaller than D in general and could be 64 or 128 and so on. So given this, we compute the rows for each position. So those rows are, of course, the Q matrix. All of them would be put in this matrix as X matrix multiplied by W. By the way, W caret Q means it's just a superscript Q. It does not a power, just to identify that this is the parameter Q. Okay. And then we have K is equal to X into W, K. And then we have V is equal to X into W, V. So, of course, Q and K are of matrices are of size so basically X is T by D and W is D by DK. So this would be in general be T into DK, and V of course is T into DV. So V of course is a subscript. It's not it's identifying that this is a parameter V. All right. So from these roles, we then compute the dot products and then find the alphas, which are the attention weights. And all of those weights can be done in one computation, which is written as self-join, or sorry, self-attention. So you can, and this is done through a softmax. This is the non-linearity. So softmax comes here. So remember previously koi non-linearity koi nahi thi. So this is the non-linearity here. And this is softmax applied on the Q, K transpose. This T is transpose. And then we also normalize it by the SQRT of DK. So this actually, in this expression involves multiple operations. The first, of course, is Q multiplied by KT. So this would give you a matrix. So this would give you a matrix of Q is T into DK. And so this would be a matrix T into D. Okay. So this matrix, let's say I call this matrix A, Q into K, T. So this matrix A is matrix of size T into T. Since this is a causal or backward looking transformer, we do not, for example, want to compute Q, let's say 3 into K4 for the next word in the sequence. We are only looking at Q3 with K3, Q3 with K2, Q3 with K1. So this matrix A would have all of these Qs, these multiplications. So we would like to, and the multiplications for a particular Q with a particular K with a greater value for the index would be on the upper triangle. So we don't want to compute that, because that would mean that we're looking at the next word, which is not required or not desirable for many applications like PS tagging or language modeling. So we like to mask that or zero it out. So in other words, जो आपका जो A matrix है, its upper triangle is zeroed out or set to minus infinity. Okay? So these values are not used. So let me draw this. So जो matrix है आपका, ये matrix है A. अब इसके जो अपर ट्राइंगल है, दिस इज ऑल सेट टू माइनस इंफिनिटी, ओनली द लोअर ट्राइंगल रिमेन्स। अब लोअर ट्राइंगल में कोई भी एक रो जो है, सो इसमें जो वैल्यूज हैं, दिस इज नॉर्मलाइज थ्रू सॉफ्ट मैक्स। हर रो को सेपरेटली सॉफ्ट मैक्स से नॉर्मलाइज करें सच दैट इट सम्स गोज टू 1। सो दीज rows are then the alphas for that particular I. Row I है, J of course goes from 1 to I, डायगोनल तक जाता है। इंफिनिटी डायगोनल का बार वाला पॉइंट वैसे ही हमने इंफिनिटी कर दिया, वो हम यूज नहीं कर रहे। सो दीज आर द अल्फा, दीज आर द टेंशन वेट्स। एंड ऑफ कोर्स ये आफ्टर वी डू दिस द नॉर्मलाइजेशन, रिमेंबर एसक्यूआरटी डी के से नॉर्मलाइज भी किया हुआ। सो ये सारी ऑपरेशंस उस एक इक्वेशन में हो रही हैं सेल्फ अटेंशन में। ए मैट्रिक्स बन रहा है, ए मैट्रिक्स का जो अपर ट्राइंगल है वो सारा माइनस इंफिनिटी कर दिया, उसका हर एक रो लिया अप टिल द डायगोनल, उसको पहले नॉर्मलाइज किया एसक्यूआरटी से डी के से, और फिर उस पे सॉफ्ट मैक्स ले लिया। नाउ द फाइनल matrix A that you get after all of these operations would contain alphas for each row, in each row. ठीक है, ठीक है, of course up to not beyond the diagonal. So these are the alphas. So once you have the alpha, then you can compute the activation at each position as at any position I as basically simply the weighted sum of the values weighted by the attention weights. What are those? Alpha ij into, of course, alpha is a scalar, v is a vector, vj, and of course, since we are talking about a causal or backward looking transformer, j is always less than equal to I. So this is the output that is computed for each position by the transformer, by the self-attention mechanism in the transformer block. Now this output is then now forwarded to any feed forward layer. There could be multiple, but let's assume that it's directly forwarded to the output layer. Then you get basically the output yi, okay, as some output activation function, let's say f or g, w ya into a I plus by. So this would be now be the output at the position I. So all of these outputs, all of these activations as well as the outputs are computed at once. There is no sequence. हम वेट नहीं कर रहे कि पहला वर्ड दिया, दूसरा वर्ड दिया, तीसरा दिया, and so on. All the words were given together as X, the capital X. And all of these A's and Y's were computed at the same time. Okay? And these A's and Y's are based on the context preceding that particular position. Remember, जो standard RNN में context हमेशा preceding होता है. Okay? So this is the basic single transformer block with a single output layer attached. So oftentimes in practice, we will have multiple self-attention heads in a single transformer block. So this, what I've written so far is a single transformer block, but with one attention head. So usually we'll have multiple attention heads. And what is the motivation behind this? The motivation behind this is that each attention head could cater to perhaps a different piece of information in the sequence. For example, one attention head may be adapted to learn, let's say, semantics, and another uh, attention head may be adapted to learn grammar, and another attention head may be adapted to learn maybe world knowledge, which is also maybe, let's say, sequence dependent. Other might be focused on discourse. Discourse is how a story is built up in a written passage. So all of those attention heads would then work in parallel, independently. तो इसलिए जो आपके जो पैरामीटर्स पहले मैंने लिखे थे, so W, Q, so now you will have different multiple heads, so all of them would have a different parameter वो I से हमने index किया है. I in general would be 1 to H. So there could be H number of heads that are run in parallel, and H can be usually in the maximum in the dozens, 12, 24 usually in practice so far. So हर एक parameter WQ, WV and WK would now be different for each attention head. So now also, as I mentioned, जो DK जो था वो different रखा हुआ था हमने, और DV भी different रखा हुआ था. Usually these are, as I said, D, let's say example लेते हैं 512 है. So DK is equal to DV, let's say ये हम 64 रख देते हैं. ठीक है? So it means that the output that you get, the A that you get, AI that you get, is of size 64 from each head. ठीक है? हर एक हेड से जो हर एक पोजीशन का आउटपुट आ रही है वो 64 साइज का. So and then of course there are H heads, so you concatenate still not right, but concatenate is for each head, for all heads. ठीक है? So let's say आपके पास, अगेन मैं A को अब हेड्स के साथ डिनोट करता हूँ. एक I हेड है, ये I यूज कर रहा हूँ हेड के लिए, ये T पोजीशन के लिए यूज कर रहा हूँ. ठीक है? So for the Tth position, the ith head would give you an output A. So let's say we have 4 heads. तो आपके पास A1 होगा for the Tth position, you have A2 होगा, आपके पास A3 होगा और A4 होगा. इन सारों को concatenate कर देंगे to give you A at position T by concatenating all A's. ठीक है? So which means that the output after concatenation would be H into 64 in this example. H let's say 10 है तो 640 हो जाएगा. H 8 है तो ये 512 वापस आ जाएगा, which is the original input. ठीक है? So if this is larger than, that's not an issue. If it is larger than the input, तो we will still be feed forwarding it through some feed forward layer. वो उसको छोटा करता जाएगा until you go to the output. ठीक है? So sometimes वो जो छोटा करने वाला पार्ट भी वो डायरेक्टली इस अटेंशन मैकेनिज्म में ही डाल देते हैं, और उस पैरामीटर को, जो प्रोजेक्टिंग पैरामीटर है, उसको WO कहते हैं आउटपुट के लिए. ठीक है? बट एज आई सेड, दिस इज नॉट एंटायरली एसेंशियल. आपने जो फीड फॉरवर्ड लेयर में गुजारना, वहां से भी वो स्क्वैशिंग हो सकती है. But if you want to bring it back to original size D, you can then pass it through WO. So उस तरह क्या होगा, बेसिकली आपके पास WO into A जो होगा वो आपको फाइनल A दे देगा. Of course WO would then be of size जो इनपुट था, आउटपुट आप डिजायर कर, आउटपुट साइज ऑफ कोर्स वुड बी D. ठीक है. So multiple attention hands in parallel, all the outputs are concatenated. Let's say एक का आउटपुट इतना है, दो का आउटपुट ट्वाइस हो जाएगा. अब उन दो का ट्वाइस को हमने फिर वापस फीड फॉरवर्ड लेयर्स में छोटे करते गए, या एक एक स्टेप लीनियर ट्रांसफॉर्मेशन करके थ्रू डब्ल्यू ओ ओरिजिनल डी तक लिया एंड देन थ्रू द फीड फॉरवर्ड लेयर. ठीक है. So this is essentially the transformer, the causal transformer. So now let's quickly look at some applications. Of course, I missed one thing. जो आपके axes हैं सारे inputs, they are usually embeddings. But for when we construct the X, the capital X, जिसमें sequence 1, 2, 3, 4, 5 है, हर एक position में हमने एक position embedding भी add करनी है, so that the network knows कि ये वाला word पहली पोजीशन में आ रहा है, ये वाला दूसरी पे, तीसरी पे, एंड नेटवर्क आल्सो कैन डिटरमिन द डिफरेंस इन पोजीशन बिटवीन टू वर्ड्स. सो द पोजीशन एम्बेडिंग कैप्चर्स दैट इंफॉर्मेशन. ठीक है. सो दैट्स हाउ यू प्रिपेयर द इनपुट. लेट्स से एक वर्ड है लिव फॉर एग्जांपल, इसकी आपने एम्बेडिंग ले ली, लेट्स से वर्ड टू वेक की एम्बेडिंग ले ली, इसमें आपने फिर ऐड किया, सो वर्ड टू वेक of live plus position. Of this position embedding would be different. If this live occurs, is the first word in the sequence, then position embedding, first position embedding add किया जाएगा. If live is the fourth word in the sequence, the fourth position embedding add की जाएगी. But this would give us the final input to the network. So now let's look at how this transformer works for language modeling, and that would help you understand things somewhat better even. So language modeling, of course, is to predict the next word given the previous context, okay? Preceding context. And so far we have looked at the causal transformer, which only considers the preceding context, okay? So in this case, so how would we, let's say we have so we want to use a transformer to learn the language model. So let's say you have a sentence, I live in Lahore. So this entire sentence is fed into the network at once, not one by one. So one I जो है वो first position पे आएगा, live second position पे, in third पे, Lahore fourth पे, ये capital X बन जाएगा, input जाएगा, पूरी metric processing होगी और सारों की output इकट्ठी आ जाएगी, Y1, Y2, Y3, Y4. A1, A2, A3, A4 के बाद Y1, Y2, Y3, Y4. ठीक है. And of course, you know the true values, and Y1, Y2, Y3 is a softmax over the vocabulary. तो वो loss निकलेगा और उस loss से फिर आपका network update होगा. So that is training. ठीक है. So training में update क्या हो रहा है? All those W's, WQ, WV, WK, and if you are using WO as well, plus जो feed forward layer में जो आपके weights होंगे, जैसे WYA है output layer का. So all of those weights will be updated by minimizing the loss function using the stochastic stochastic gradient approach. Okay, so that is training. So once you have the trained network, अब उसको use आप कर सकते हैं for perplexity computation, or in other words, finding the probability of new sentences. So this was so we have talked about training. So training, as I said, each sentence is processed all at once. You get all the losses. Loss का sum हो जाएगा, back propagation हो जाएगी, and so on. आपका update हो जाएगा network. So once you have trained the network, then you can compute for new sentences. So let's say you have a new sentences, he lives in Karachi. So now this whole sentence would be fed into the trained network. ठीक है, अब उस ट्रेंड नेटवर्क में हर एक पोजीशन पे ही की पोजीशन पे y आ जाएगा, लिव्स की पोजीशन में भी y आएगा, ऑफ कोर्स द मैक्स वैल्यू आग मैक्स करेंगे हम. So all of those probabilities, if you multiply them, you'll get the probability for this sentence. So I'm going to write this as, for example, y is, so let me write in terms of probability. So probability of, yeah, I think I just write it in terms of y. So y1, so this is a probability into y2 into y3 into y4. So this would be the probability of the entire sentence. What is y? This is the max probability that is outputted at that position. Okay. So it's not the word, it's the probability. I'm using it here as a probability. So इस तरह आपके पास कोई भी सेंटेंस है या लॉन्ग पैसेज है, वो सारा आप फीड इन करें, हर एक आउटपुट की आपका प्रोबेबिलिटी आ जाए, मल्टीप्लाई ऑल दोस प्रोबेबिलिटी, यू विल गेट an estimate for the this sentence. If this estimate is low, of course, then it means that it doesn't belong to that language. If it is high, then it does belong to that language. So that is, you can say, finding probabilities of sentences. You can also use it for generation, as we did discuss for RNN as well. So for generation, we will be using the auto-regressive type of approach. So let's say आपने generate करना है, you start with a transformer that doesn't have any input. तो पहला जो output है, of course input network आपका randomly आप initialize कर लें, पहला output y निकलेगा, वो distribution होगी, ठीक है. उस distribution में से आप let's say max आपने ले लिया, वो word आपके पास आ गया. So let's say वो word मैं कहता हूँ D आया पहले, ठीक है. अब in the next stage, अब आपने आपके ट्रांसफार्मर में इनपुट में आपने पहली पोजीशन में डी दिया और फिर y2 का आपने एस्टिमेट लिया. दैट्स आल्सो अगेन ए डिस्ट्रीब्यूशन, और उस डिस्ट्रीब्यूशन में जो भी मैक्स आपने लेना था, लेट्स से आपने ले लिया, विच इज लेट्स से दी हाउस, लेट्स से आ गया आपके पास. अब नाउ यू हैव टू वर्ड्स. अब ये आपका जो सीक्वेंस इनपुट होगा आपके ट्रांसफार्मर में, दी भी जाएगा, हाउस भी जाएगा, फिर 3 के लिए आप उसकी आउटपुट लेंगे, डिस्ट्रीब्यूशन होगी, उसका मैक्स लेंगे, वो तीसरा वर्ड आ जाएगा, एंड सो ऑन. सो दिस इज ऑफ कोर्स ऑटो रिग्रेसिव जनरेशन, बट विद टीचर फोर्सिंग. टीचर फोर्सिंग क्या है, जो एक्चुअल आउटपुट आई थी वो आपने पीछे सीक्वेंस देते गए. Okay, so this is also similar to in RNN, but now in the context of transformer, आप सीक्वेंस बड़ा करते गए. Of course, for generation आपका and for inference, you are using the model sequentially. Of course, for जब मैं probability estimate निकाल रहा था पूरे word का, पूरा sentence का, उसमें सारा sentence मैंने इकट्ठा एक दफा दे दिया, तो वहाँ sequential नहीं था. But generation के लिए, और जहाँ हम auto regressive use कर रहे हैं, वो sequential ही चलाना पड़ेगा हमको. So इसी तरह another application is, let's say for example, you're all familiar with next word suggestion. Okay, so next word suggestion, you're typing something on let's say Facebook or whatever. You have already written a few words, and then the system will recommend the next word. Okay, so this is also done in a similar way. So the previous context है वो आपका input network में जा रहा है, जो next word के लिए जो भी probability distribution है आई है, उसके जो top words हैं वो आपने recommend कर दिए, ठीक है. और let's say आपने कोई एक word लिख लिया आगे, फिर आपने अपडेट कर दिया नेटवर्क पे सीक्वेंस, with including that new word, and you get the prediction for the next word. So any questions? Okay, so let's look at another application. So by the way, ये जो application है where we are generating a word given some context, which is of course the preceding context. In this case, it's generally also called conditional generation. Okay, so we are generating conditioned on some preceding word that we know or we fix. So that's called conditional generation. Okay, so another application of conditional generation, एक तो of course यही थी word suggestion थी, and of course for random language generation. Another application is for example summarization. Of course summarization के लिए later on हम आगे भी और models देखेंगे. ठीक है, so summarization में क्या होता है, you have a passage and then after that you generate a summary of that passage. So if you want to use a transformer for this, so what would you do? So typically app, and of course we are talking about a causal transformer in this case. So we will have an input data. Let's say we have a passage which I call, let's say P, and then we have a summary which I call S. Okay? Of course, P is sequence of words, S is also a sequence of words. Okay? And of course, these sequence of words could be of differing lengths. The length का भी issue हम slightly अभी discuss करेंगे, but just hold on a little bit. So how can we use a transformer to first of all learn this and then use it for generation? So this is actually example of conditional generation also. So किस तरह के आपका जो input है x, जो हम x ले रहे थे capital X, उसमें जो पहला जो words होंगे वो words passage के होंगे, P के होंगे. और फिर after a row in this X, which is called a separator row or sep token, एक separation token हम डाल देते हैं to distinguish it between P and S, हम फिर summary शुरू कर देते हैं. ठीक है, और इसमें फिर हम जो हम करेंगे, so attention इसमें किस तरह होगी. So let's say let me just give some numbers. Let's say P की 10 है और let's say S की length 5 है. 5 words for the summary, 10 words for the input. ठीक है, so the first 10 words of the sequence would be the passage. So let's say उसको X से मैं कहता हूँ X1 2 X10, ये मेरा पैसेज है. इसके बाद जो मेरे पास आएगा एक टोकन आएगा X11, which is called a separator token. This tells us that the passage has finished and now we are going to look at the summary. So X11 जो होगा मेरा, X12 जो होगा वो मेरे पास फर्स्ट समरी का होगा. इसी तरह X13 14 15 16 X16. So the fifth word of the passage. तो ये हमारा कैपिटल X बनेगा. कैपिटल X में इनकी एम्बेडिंग्स होंगी. Of course सेपरेटर की एम्बेडिंग कोई फिक्स्ड एम्बेडिंग होगी which we define ourselves and call it the separator embedding. अब इसमें after the sep token, that is where the generation is occurring. So the self attention we can have self attention between X1 and X5, X1 and X6, and also reverse, but we cannot have self-attention between x14 and x13. Sorry. So we can have attention from x12 and to every word in the passage. Summary generate करने की previous passage चाहिए ना हमको, right? So we can have self-attention from x12 to from x1 to x10, x13 को भी x1 to x10 तक हमको उसकी self-attention चाहिए up till the preceding word. ठीक है? जैसे हम language modeling में let's say we are talking about x14, so x14 हम जब generate करेंगे तो x13 and backward सारी हम use कर सकते हैं. x13 of course एक generated summary word है, but x1 to x2 input passage word है. So that is also useful in generating a summary word. तो हर दफा वो attention हम उस पे भी लेके जा रहे हैं. So this is again an example of conditional generation, but now this is conditioned on a passage. So do you understand this point? And it can be used for summary generation. This sep token in between just tells us when the passage ends and when the summary starts, and maybe you can add some additional checks to make sure that you do not do any incorrect attention across this separation. Okay, so every word at any given point would, and of course after the sep, would attend to all the words before it. But any word before the sep can attend to words after it as well. But that is kind of irrelevant because we'll be generating after the sep token. So you will train in this way, and then of course जब आप टेस्ट कर रहे होंगे, टेस्ट भी आप इसी तरह करेंगे through teacher forcing, just like for language generation. But of course with the whole passage as input, and then whatever you have generated also as input. So much of this discussion, I think today and maybe in the next couple of lectures, involves a bit of visualization and how you can apply a particular application using these models. So usually मॉडल्स वही हैं, सिंपल मॉडल्स जो हमने डिस्कस कर लिए हैं. ट्रांसफॉर्मर का मॉडल आगे जाके हम बाई डायरेक्शनल ट्रांसफॉर्मर भी डिस्कस करेंगे, बट उसको फिर थोड़ा सा रीशेप करते हैं एप्लीकेशन को, और वो ट्रांसफॉर्मर यूज कर लेते हैं या वो मॉडल हम यूज कर लेते हैं. सो मस्ट ऑफ NLP इज लाइक दिस nowadays. So this was an application in summarization, and there could be other applications as well. And we'll come back to summarization again later on. For now, let's move on to another architecture, which is more powerful, especially when you have input and output sequences that are of different length. Remember जो ऊपर हमने summarization अभी discuss की, इसमें भी input थी हमारे पास passage, output था summary. They were of different length, but we were able to use a transformer, which is a single model, effectively. But we have another model that works well when the input and output sequences are of different length, which is basically called the encoder-decoder model. And since we are talking about sequences, so usually this is also sometimes called a sec-to-sec model or sequence-to-sequence model. The input, which is encoder, the input is a sequence, the output is also a sequence. The input goes through the encoder, gets encoded. It becomes the conditional input to the decoder, and the decoder then decodes and generates the output. Okay. So output is also a sequence, input is also a sequence, but now the whole input sequence gets processed first and then goes through the decoder also as a sequence while generating the output. So So these models are very appropriate when input and output okay. So POS tagging, for example, or NER, all of in that input and output sequences are of the same length. But for example, machine translation, for summarization, for paraphrase generation, for question answering, generally the input and the output sequences would be of different length. Okay. So we will discuss this model in the context of machine translation. And this is, of course, chapter 10 of your textbook. So we have primarily covered all chapters till chapter 10 now, 1 to 9. So this is chapter 10, machine translation, and we will be discussing the encoder-decoder model in this context, in this application. So just a quick overview of what machine translation is, and then we'll go back to the encoder-decoder model. So machine translation is basically mapping an input language to an output language while maintaining, you can say, informativeness. So just like humans, we would like to translate information from a language that we don't understand to a language that we understand. So machine translation actually in general has a number of applications. The first most important application is information access. So not all of us speak all languages. And of course, information sometimes appears in other languages. So if that language is not known to us, that information would become useless to us. So we like to translate that information to a language that we understand. So we will be able to then access that information. So one main application is information access. And of course, information access, you can think of many, many real world applications. So I don't think so I need to mention those. So another broad application is for assisting human translators. So oftentimes human translators are enlisted to translate documents and other pieces of information from one language to another language. So to assist them, we will oftentimes generate a first translation using automatic machine translation. Okay. So that's another key application of machine translation. And then, of course, you can think of many real-world applications that can benefit from machine translation. All of you are familiar with Google Translate and other translation engines, which have helped us to travel to places where we do not speak their language, but we are still able to communicate with that people. If you go to China, for example, you can take your Google Translate, and Google Translate would translate your English to Chinese. The Chinese people would then understand that. They will write back in Chinese, and the Google Translate will translate back it into English. Okay. So let's say let's say we have a couple of languages. Let's say Urdu and English, for example. So let's say I write wo लम्ज में पढ़ता है, for example. So this is in Urdu. So if you want to translate this into English, the correct translation for this would be probably he studied at LUMS. So you notice that we have translated this and all the information is captured, as well as both the sentences are in correct language, meaning that linguistically and semantically and grammatically correct in the two languages. But languages have different rules. The ordering of words will be entirely different in the two languages. And so people in the past had studied these variations in pairs of languages quite extensively. And then they used, after studying these variations, they then developed some rules, and based on then those rules, they were then able to do some translation. So I would say since the mid 1990s or up till the mid 1990s, rule-based machine translation was widely popular. Rule-based automatic machine translation was widely popular. So rule automatic machine translation. So this was popular till, I would say, around 1995. So since 1995 till about 2010, statistical, or you can say even machine learning based machine translation became popular. So statistical auto machine translation, this became popular, I would say, from 1995 to around 2010. So this was the most popular way of doing machine translation. And the earlier machine learning based machine translation techniques were based on, for example, the Markovian models that we talked about earlier, or the conditional random field, which is a discriminative probabilistic model. So most of the successful models in this period were based on machine learning, maybe augmented with some rule basis for machine translation. But since 2010, neural network based machine translation have become the dominant way of machine translation. So 2010. Okay. And of course, this is all due to the popularity of sequence models in natural language processing. So we have been studying sequence models for the past 2-3 weeks now. So rule-based techniques are good at understanding languages and their differences, and but they do not generalize well. And languages often have a lot of variety. So rules do not apply in all scenarios. So that's why rule-based techniques often failed. So we would usually like to learn from the data itself, large amounts of data. So that led to basically the statistical techniques first, and then now the neural network-based techniques for machine translation. Languages can differ in various ways. I think there is a section in their textbook on differences in languages. I think I will not discuss that, more of linguistic. You can go over that at your own time. So they have identified differences in terms of morphology. They have identified differences in terms of grammar. So for example, some languages are what they call it as subject, verb, object. For example, English is subject, verb, object. Verb appears between a subject and an object, which usually are nouns. So example, of course, is English. And some other languages are basically subject, object, and verb, meaning that you have a subject and then the object, both of them being nouns, and then you have a verb that is connecting those two nouns. So there are many languages, this category, Urdu is one of them. Okay? So again, ordering would be different in different languages based on this classification. And as I said, there could be various other differences, morphologically rich languages. For example, Urdu is morphologically rich. Even nouns and verbs would be different for different settings. While for English, usually don't have different variations for verbs for different settings. In other words, basically words have different forms, much more different forms in Urdu than in English. Arabic, of course, is notoriously morphologically rich. You have tons of variations for each word in Arabic. So so that's other differences. Other differences could be lexicographic as well, lexical. In other words, some languages have precise words for precise phenomena, different phenomena, while other language may not have a unique word for a particular phenomena or a particular concept. So you can think of, for example, कुछ words होते हैं पंजाबी में उसका exact word मिल जाता है, उर्दू में नहीं मिलता उसका. So there are examples like that in multiple languages. So these are lexical differences. So in any case, all of these differences are highlighting the difficulty in rule-based techniques, and also in general difficulty in data oriented techniques as well, because you'll have to learn a lot of things that might change in different settings. Okay. So that was just a quick introduction. Now let's go back to our encoder-decoder model. Okay. And let's start with the simplest scenario. So let's say our encoder is an RNN. It's a sequence model, right? And I can call it RNN-E. Of course, you can denote it by something else. And then we have RNN-D for the decoder. So there are two separate decoders. These decoders are one after the other. These RNNs are one after the other in series, or what they call as stacked. Pehla RNN processes your input language word by word. Okay. So at each position, it outputs, of course, an A. And from that A, you can also output a Y if you want to, but that's actually not required in this case. So at each position, you get an A. And then at the final position, you also get a final A. So that final A, for example, if I have an input sentence, he studies at LUMS. तो पहले आप ही इनपुट करेंगे, फिर स्टडीज इनपुट करेंगे, एट इनपुट करेंगे, लम्स इनपुट करेंगे. जब लम्स इनपुट करेंगे तो आपके पास फाइनल एक आउटपुट आएगी A4. ठीक है. So this is the final output that contains information for all the preceding context. He studies at and LUMS. Okay. So this A4 is now, so A4 now becomes the first input, I would say contextual input to RNN-D, the second RNN. So contextual input क्यों मैं कह रहा हूँ, because of course एक दूसरी input भी होती है जो, remember RNN में एक आपके पास A होता है, A0 होता है, X1 होता है. So now A0 now becomes this. So if we talk about RNN-D, इसका जो A0 है, this would be A4 of the previous network. ठीक है. So what does this mean? कि previous सारी information जो input language की थी, which was in A4, now gets into your A0. ठीक है. अब during training, of course, आपके पास उस sentence का सारा उर्दू का भी है. So remember, we are translating from English to Urdu, let's say. तो इसका जो reference translated sentence जो उर्दू में होगा वो लम्स में पढ़ता है. ठीक है ना. Of course, also notice that the input sequence length, if you tokenize through words, is different from the output sequence length. Output sequence length लंबी है, वो लम्स में पढ़ता है. ठीक है. And he studies at LUMS is 4 words, वो LUMS में पढ़ता है is 5 words, if you tokenize, of course, as I said, using space delimitation. अब जो इस RNN-D को जो जाएगा, A0 जाएगा, of course, which is of course A4. and then we have x1. This would be the embedding for wo. ठीक है? And this should actually x naught be, because we are doing generation here. ठीक है? So a naught आपके पास आ गया. इसको भी नॉट कह देते हैं या वन भी कह सकते हैं, डिपेंडिंग ऑन हाउ यू लेबल दैट. So this can be all zeros. ठीक है? So this will produce a distribution over the target vocabulary, which is in this case Urdu, and we will now match that distribution with the actual word, which is of course wo, and this would be the loss. If there is a loss, of course, that would be quantified through cross entropy and then used to update the whole network behind it. But usually we'll pass the whole sequence multiple times and aggregate the losses before updating the network. ठीक है? तो ये पहला हमारे पास एक जनरेशन होगी. अब नेक्स्ट जनरेशन में हमने अब ऑफ कोर्स इसका अपना भी एक RNN का एक A होगा. जो ऊपर A नॉट था, अब A1 आपके पास आ गया, which has information for A naught as well as जो आपने x naught दिया था, which is of course zeros. But now we will be giving x1, which is actual wo. This is of course the teacher forcing thing while training. ठीक है? And then we generate the second word wo, lums. The second word should be lums. If it is not, then there is a loss, and so on. Okay. So usually we will give several sentences before we and aggregate the losses and then do an update, which is of course batch updating. Okay. We don't really update after each loss. Okay. So the decoder is actually doing contextual generation, and decoder is on the Urdu language. The encoder is on the English language. And the contextual generation means that it's context on the input that comes from the encoder. And these models are also what they call trained as end-to-end. Generally, a term used होती है for deep neural networks, where you have multiple layers. So एक end से जो loss बनता है वो सारा propagate होता है back तक to the start of the network. So these are called end-to-end training. So इस case में भी end-to-end है. Loss आपका generate हो रहा है decoder में. अब वो decoder को भी update कर रहा है, which has its parameters, and it's also updating the encoder as well. So your back propagation जो जाती है, it goes across the two networks, across from the decoder to the encoder. All right. So we have about 15 minutes left, so let's try to wrap this up. So this was training. So what would happen if you are using it for machine translation? So once you have trained the network, you have learned all the parameters of the RNN-E, which is encoder, and the RNN-D. So all the parameters are there. So when you want to do a translation, you feed in the input language one by one. And of course, after you have fed in the entire input language, it goes to the decoder. Now the decoder now does auto-regressive generation, just as we did for language modeling, but this is of course contextual auto-regressive generation and context on the input. And generation, as we discussed for language modeling, is the same. It's done in the same way. आप उस पूरी generated sentence का probability निकाल सकते हैं, या आप एक एक्चुअल प्रिडिक्शन करवा से जनरेट कर सकते हैं सेंटेंस यूजिंग मैक्स प्रोबेबिलिटीज, बेसिकली टेकिंग द आर्गमैक्स. Now, इसमें there are a number of things that we need to think about. One of the issues that arises is, remember we said A4. So A4 theoretically contains information of all the input sentence, starting from the word he studies at LUMS. If the sentence is large, then of course the information of the first word might be kind of suppressed. It's very far away, because it might be overwritten by some of the newer words that you have fed into the network. Okay. So one way to overcome this is we sometimes use a bi-directional, as we discussed, RNN for encoder. Okay. So if you remember what was a bi-directional encoder, RNN, so you have an RNN, two RNN in parallel, not in series. One RNN processes from left to right, the other RNN processes from right to left. And let's say all of them process to the end, meaning that you have processed the right to left to the first word, and you have processed the left to right to the last word. Then you concatenate both of these outcomes and then feed into the decoder. So now at least you will have the faraway information as well as the closer information in two separate vectors that are concatenated, and hopefully some information loss might be reduced. Okay. So that is one way that you can reduce this issue of information loss through long sequences. In long sequences, use a bidirectional encoder. Another way is to have cross attention. So remember we talked about attention before, but that was self attention. Now this is cross attention. So what is cross attention? So cross attention is attention between an output of the decoder and all the outputs of the encoder. So what was self attention? So self attention क्या होती थी? For example, हम self attention x3 की निकालना चाह रहे थे. तो x3 का हम, of course in the causal model that we discussed, x3 का हम relatedness x2 से भी देखते, x3 के साथ भी देखते थे, x2 से भी देखते थे, x1 से भी देखते थे. ठीक है. So in the case of cross attention, let's say so we are now going to have attention between the activations of the decoder and the encoder. So let's say activation of the decoder की मैं बात कर रहा हूँ. So यहाँ मैं D लगा देता हूँ और first activation of the decoder. ठीक है. This is a decoder. So we would like to have a relationship between this activation and the activations of all the encoder activations. So इसका फिर क्या होगा? Let's say E1 के साथ भी, E2 के साथ भी, E3 के साथ भी, और E4 के साथ भी. So maybe the first word in the translated language is more related, or is more related to some other word. It's not, it's probably is more related to maybe the last word or the third word or even the first word. अब वो relation किस तरह है, we'll allow the cross attention mechanism to learn it automatically. तो जो self attention हमने पढ़ा था, it's exactly the same way. But of course now this is between the activations of the decoder and the activation of the encoder. इसमें भी parameters होंगे, and you will get alpha, which are weighing mechanism. You will get outputs which are weighted weighted by the alphas. And of course, you'll give greater weight to, let's say, a word if that word has a stronger relationship with a particular position in the input. So for example, जैसे हमारा क्या था, he lives, sorry, he studies at LUMS, वो LUMS में पढ़ता है, ठीक है ना. So of course, LUMS in English is the last word, LUMS in Urdu is the second word, ठीक है ना. So self attention or cross attention in this case would be able to track such relationships. And we allow this to be done adaptively as part of the training process using the cross attention mechanism. ठीक है. So you can even think of this cross attention mechanism as some form of skip connection or residual connection, because जो आपका decoder है उसकी एक particular output is now connecting to a particular output of the encoder. मतलब connecting in the sense that it's taking information or directly from there without going through the intermediate process of the encoder. Okay. So attention mechanism हमने इसको build कर दिया so that words can have direct relationships in addition to the information that is passed on through the final encoded vector A4. So I think we are running out of time. So in the next lecture, we will discuss beam search, which is a way of getting optimal generations or close to optimal generations. And then we will move on to contextual embeddings and the BERT model, which would then be chapter 11 of your textbook. Okay. So we will also have our last quiz on Thursday. And then, of course, next week probably would be primarily the last week of studies, and we might have one lecture in the following week, but primarily next three lectures will be the last 3 lectures of this course. ठीक है. So any questions?